Everyone, welcome to week 3. So far you've learned about qubits, quantum information, Dirac notation, how to manipulate qubits, what it means to read quantum information in terms of that quantum measurement. And now we're going to get into the nitty-gritty, the meat of quantum information, and that is what happens when you combine systems together and get this phenomena of entanglement. All right, let's get started. Recall from classical computing or classical information theory that if I have 2 bits, B1 and B2, then I just write them down next to each other. That creates a bit string. So 2 bits is something that can resolve 2 yes or no questions or 1 of 4 possibilities. So this thing can be in a set that contains 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. So now there's 4 possibilities with 2 bits. An analogous thing happens with qubits. If I have 2 qubits, then instead of that being represented by a 2-dimensional complex vector space, it's now represented by a 4-dimensional complex vector space. And that means that there exists 4 basis elements in which any vector can be written as a linear combination in. So if I have a vector, it's in a 4-dimensional complex vector space. I can write it as a linear combination of 4 basis vectors, and that can be any basis, but I'm going to choose one that's a bit convenient, or some labeling that's a bit convenient that we'll use later on. So I'm going to enumerate the basis and the coefficients in binary. And that might look strange to you, but I think to a computer, counting to 4 in binary would be very natural. And these things still have to be normalized, which means the sum of the magnitudes of these coefficients has to be 1. Okay, so far so good. Now I've just done what we've done for qubits, and I've doubled everything that we're looking at. Of course, this object here, if we translate it back to linear algebra, is that one there is just a 4 by 1 complex column vector. That's gamma 0, 0, gamma 0, 1, gamma 1, 0, gamma 1, 1. And of course, you can get at these coefficients by looking at inner products with the original vector. So the inner product between these basis elements and the vector. And that's how you can write these things, all these things down, just in completely abstract notation, divorced from any concrete representation, which is useful if you want to do calculations or prove things. That's for vectors. For matrices, it's the same deal. So recall that if I have a matrix that acts on a 4-dimensional vector space, it's just a 4 by 4 table of numbers, and that table is labeled by those basis elements. So a square matrix here, and I'm doing this explicitly just because you'll see that the notation can get a bit cumbersome. So the first element is labeled by the row and the column. So that's 0, 0, and I'll put a comma in there just to distinguish the row and the column. And the next one is 0, 0, 0, 1, 0, 0, 1, 0, and finally 0, 0, 1, 1. Okay, and then the next row starts with 0, 1, and the column is 0, 0, and so on and so forth for that row. so on and so forth for that column. And finally, we'll get at the very bottom right, the 1, 1, 1, 1. That's the explicit matrix representation of any matrix in acting on a 4-dimensional vector space, so 4x4 matrix. We can write that in Dirac notation in the same way that we did before. So the U 0, 0, comma 0, 0 goes in front of the projector onto that basis state, and 0, 0, comma 0, 1, you can see that the comma separates what's going in front of the ket and the bra for these outer products as before. And we could keep going and going and going and going, and then eventually we would get to the final one, which is 1, 1, comma 1, 1, and the outer product, which happens to also be the projector onto the this 1, 1 state. Remember, we're just counting. We're doing the same thing we did for qubits, except instead of a 2-dimensional vector, we have a 4-dimensional vector, and we're going to count in binary instead of your preferred method of counting. Now, you can see already that these indices are getting a bit cumbersome, and the sums, I'm already skipping terms. So at this point, we might as well move over to a more convenient way to write out sums, which is the summation notation. So a vector can be written as a sum over the indices that label the coefficients and the bases. Now, here we had binary, so we could have one index that goes over all binary strings of length 2, or we can label it as 2 binary numbers. So that's the way we're going to do it here. We have 2 binary numbers, and so they take on values 0, 1. And if we look back up at the definition, it's gamma, the indices, and then the basis vector with the indices in it. So you can see that each of these terms looks identical except for the index that happens to be there. So gamma, I, j, and then that ket that's labeled ij. And that's a much more compact way to write down a state. And the matrix, which I didn't even write out in full, can now be written in a similar way. So I have 4 indices now. I have I, I have j, and I have k, and I have l, and that set of indices make up 4 binary variables. So this is I, j, comma, k, l. And if we look just above here at the top, we have that the second 2 indices go with the bra, and the first 2 indices go with the ket. So I, j, k, l. Right. So here we have the state vectors and the matrices written out in summation notation, and if we wanted to increase the dimension, now it's really easy to see what we do. We just allow these indices to range over a larger set of possibilities. So we had states and the way we change states, and the last thing was how we read the quantum information, which was the measurement. So the picture we had was some state, and it represents this qubit, which is a line, and then it enters this box which reads the quantum information, and the box had outcomes that would be labeled by bases, and the possible outcomes correspond to each of the basis elements. Now, we said that the probability of seeing outcome 0 given psi would be the inner product of 0 with psi squared, and that is psi 0 times its complex conjugate. That's the definition of the magnitude, or the norm. So that upper line is equal to this lower lines, because we have a number times its complex conjugate. And this thing is the inner product of psi with itself, but sandwiching this projector 0. So we can rewrite this probability rule as this inner product rather than this extra thing that comes along, this modulus squared. And recall, we also said that after the measurement, the state has collapsed into that state that we observed. Now, this can be written in terms of the basis vector as well. So instead of saying if 0 was observed, then the state collapsed to 0, or if 1 was observed, the state collapsed to 1, we can just say that, well, for the 0 case, we can see that this is the projector acting on psi, and that part there, let's just remind ourselves that this is 0. Okay, so it's the state that we want, and it's being multiplied by this inner product between 0 and psi. So that's just a quick aside. So it's not exactly equal to this. We have to cancel out that factor, and the way we do that is we look at that probability, because it has two factors of the inner product of 0 and psi, we take a square root. So the update rule in general is written in this way, and this projection, I think, kind of more encapsulates this notion of collapse. So we're really projecting the state onto the outcome we observe. Okay, so that's for a single qubit, but now we have a four-dimensional vector. What does reading the information of such an object look like? Well, it's the same deal. We have a measurement. It's specified by basis. For example, this one we've labeled here. And these are all states, and so then they're all associated with their own projectors. And just to be clear, they're each just the outer product of this ket labeled with that same label and the raw. So there's four outcomes, and it's a bit string, ij. We start in psi, and the probability is the inner product of the state, kind of it's not a technical term, but I think at some point it will be, the sandwich, the psi sandwich here. So psi is sandwiching the projector. You'll hear that actually quite often. And the state, after we observe outcome ij, collapses to the projector onto ij, and we're dividing by the square root of the probability. And that's just so that, again, the state becomes normalized. Okay, so we see now in the end that a lot of this is just the same in the sense that we're using the same mechanics of linear algebra, but just on a 4-dimensional vector space rather than a 2-dimensional vector space. But I haven't answered the question, what actual vector in this 4-dimensional vector space corresponds to the state of 2 qubits if I've been given the state of both of the qubits separately? So that we'll see next.